The IRF deconvolution option is used to remove a known IRF for instrument response from data prior to fitting or other analysis. The removal of the instrumental distortions in a pre-processing step allows for fitting very fast closed-form peak models to the data. This procedure is most useful for chromatography data where all of the best IRF-bearing peak models are convolution integrals that don't have closed-form solutions. For most spectroscopy data, there's a closed-form void that can directly manage the convolution of the Lorentzian and Gaussian broadening. For most spectral data, there's little benefit from a pre-processing deconvolution step. The chromatographic data shown here are from a 3-component reference standard that was used over the course of several years. These data sets have already seen a baseline correction, but they have otherwise not been changed. We will use the View and Compare Data option to evaluate the consistency of the chromatography over these several years' time. As you will note, the areas of the 3 components of this standard are approximately equal across the different runs across time, but the elutions varied somewhat. We might thus expect some variation in the estimate of an IRF as a consequence. We will select a fit previously made of these 12 data sets. It uses a once generalized HVL model with a GE IRF. This is the instrument response function that contains the sum of a half Gaussian probabilistic distortion and a first order exponential kinetic delay. The 12 fits range from 3.2 to about 17 parts per million statistical error. Excellent fits. If we look at the numeric summary and select the average multiple fits option, we can scroll to the bottom, and here we will find the average of the 3 IRF parameters. You can see here we have a 0.036, 0.076, 0.95. This means 95% of the area of the IRF consists of this first component, the half Gaussian. The CV is coefficient of variation is given as a percent, and you can see here we're looking at 4.5%, 8.5%, and a little over 2% for the 3 values. So you can see we have a very, very tight estimate of the IRF across 3 years' time on this individual separation. So long as there are no changes in the instrument, the injector, flow path, column, detector, in the mobile phase, in the run conditions, flow rate, temperature, or in the prep, these 3 IRF parameters are unlikely to change in any future similar separation. We will first enter these values in the IRF deconvolution procedure. We'll make sure we have the GE IRF that we're deconvolving right, and we will put in these 3 parameters that we averaged historically, 0.0366, 0.0766, and 0.943. Apart from these 3 parameters, the only other issue is the Fourier filter that is used to remove the noise that is produced by the deconvolution. There's an automatic procedure that will typically do what you need it to do with very little effort. So you can see here the yellow curves are the deconvolved or sharpened curves. The blue curve is the original data. And this is the difference between a perfect instrument with no instrument response function and the actual data coming from the instrument where the instrument response function has produced these distortions. Once you know the IRF of a given separation, it simplifies considerably the fitting that you will do after the fact when you do this pre-processing step. So we're going to be fitting the yellow deconvolution data now. I simply click OK, and now we have a new data layer that consists of the deconvolution. We'll go out to the local maxima option. We'll pick the Gen HVL without an instrument response function. the closed form version of the model. We will allow the width and the chromatographic distortion to vary, and it's as simple as selecting the peak fit, selecting the the most sophisticated of the strategies for the fitting, clicking OK. Took less than a second for most of the fits. We will review the fits, and we see here that the deconvolution, for one, we are looking at an average across 3 years. In the other case, we are also adding some noise from the deconvolution procedure. However that is the case, we do have some very good fits that vary. Here you can see the average is about 37 parts per million error. And if we were to look at any one of these fits, you would see a very, very tight track of the fit, and some portion of that error are these additional little blips along the baseline that are coming in from other components that are present at a trace level. So a superb fit, very little time, very, very good convergence on the fitting, virtually effortless, and that's the benefit of knowing what your instrument response function is prior to the fitting. At this point, I'm going to create a new copy of the data without the deconvolution we just did. I now have a new data layer that consists of a data prior to deconvolution. I'm going to go into the deconvolution procedure, but now instead of using the known values that we pulled from those prior fits, I'm going to just increase these values somewhat. As you see here. And you can see now the deconvolution goes well below the 0 of the data. That's what you typically see when the deconvolution parameters are too high. What the genetic algorithm does, it will optimize to try to produce the maximum amount of 0 baseline that's present. So we're going to, within this tolerance of 1%, we're going to try to produce as much possible baseline as possible by varying these 3 parameters. It's as simple as just clicking the optimization, and you see something reasonably close to what we had in the nonlinear fitting that we looked at. In this particular case, each one of these will have a different set of parameter values based upon the optimization, but you can see here we're not terribly far from the 0366, 0766, and the 0.93 that we put in from the fit. So in many cases, this algorithm works exceptionally well for giving you the true IRF as in an alternative algorithm to the nonlinear modeling. It can be used as a cross-check, and it's also a very convenient way to deal with data that experimental data that varies where you're unlikely to have the fitted information. So in this particular case, we're just going to click OK. We're going to accept the 12 deconvolutions. We're going to go out and do what we did before. We're going to go to the local maxima option. We're going to select the Gen HVL, and we're going to be fitting these 12 deconvolved data sets. If we review these, we go down and we look at our average. You can see we have 38 instead of 37 parts per million. Here you see we have very close to the same value as using an entirely different algorithm to produce the deconvolution. I want to show one more item associated with the IRF deconvolution. I'm going to again make a copy of the non-deconvolved data. We're going to go out to the IRF deconvolution, and we're going to look at the PE IRF. Horvath and Lin years ago, when they were looking at the mass transfer resistances in a system, found one of the rate steps was higher than first order. This is a 1.5 order and a first order sum, which we found to be pretty useful in a good number of actual test. It's very hard to fit, but it is very effective in this particular kind of genetic algorithm procedure. So I'm going to go ahead, and we're in a good place right here. We have the values set a good measure higher than what the actual values will be. We've got the values dropping well below 0, so we're going to bring this up close to 0 and maximize the amount of 0 baseline. We can see something that looks very similar to what we saw with the other IRF. We'll go ahead and we will accept those revisions. Each one is unique. Each one has a different set of IRF parameter values as a consequence of the genetic algorithm. We'll go into the local maxima fitting procedure. We will repeat the fitting process. We will review the fit now, and we will look at the average of these 12 fits. And you can see here at this particular case, we've got 16.4 parts per million. We see a nice improvement. An example of an IRF that may well be more correct, that is very difficult to fit in a nonlinear procedure, but works very well in this genetic algorithm. I'd like to add just a few notes about the IRF deconvolution procedure. If we look at the Fourier power spectrum, I'm going to remove the second derivative curve. You see on any one of the FFTs this point right here. This is where you're looking at the peak information, where you're looking at signal. This is where the deconvolution has produced an additional noise. In this particular case, the value is so small you could get away largely without a filter, but for many different types of chromatographic data sets, that's not the case. You will actually see this explode, where unless a filter is done, you won't see anything at all on the deconvolution. If you look at the point right here on frequency, you would say, well, 25, a frequency of 25 would be about the optimum. You can go in and you can set the frequency at the value you've determined visually. And in this particular case, you can see we'll come very close on each of these for the individual filters. So now our filter will be set at this value, and we can do the optimization there. This is what the automated algorithm attempts to do, but in this particular case, you have the option of doing this manually. This is state-of-the-art for the most widely accepted form of doing deconvolution. There are alternatives, but this is largely what is done in the science. So in this particular case, we will use that, and we will use that particular frequency as the cutoff filter for all 12 of the deconvolutions.